History is not a straight line. It is a series of long silences, followed by sudden, violent explosions of progress. For nearly 60 years, robotics lived in silence. We saw novelty machines, toy dogs, and carefully choreographed demos, but the physical world remained largely untouched by artificial intelligence. Robots stayed behind cages, behind warning signs, behind glass. Then, the silence broke. This wasn't a takeover announced with alarms or headlines. It happened the way all real revolutions do, quietly, politely, and at scale. In just 36 months, the humanoid went from a laboratory curiosity to a mass-produced consumer appliance. We moved from rigid if-then code to machines that learn by watching, from million-dollar research projects to $20,000 home helpers. Today on Techtrac, we are tracing the timeline of the most significant technological pivot in human history. Why it took so long, what changed inside the secret labs over the years, and why 2026 is the year the robots finally moved in. The trace begins in 1961, inside a General Motors plant in New Jersey. There, Unimate, the world's first industrial robot, came to life. It wasn't intelligent, it wasn't flexible. It was a single mechanical arm built to perform one task. It was created by George Duvall, who invented the concept of a programmable robot, and Joseph Engelberger, who turned that idea into reality. Together, they built the world's first industrial robot and launched the age of automation. Unimate's job was simple: lift and stack scorching hot metal parts fresh from die casting machines, work that was repetitive, dangerous, and often life-threatening for humans. Contrary to popular fear, Unimate did not replace workers, it replaced risk. At General Motors, production lines ran longer, injuries dropped, and consistency improved. Humans didn't disappear, they moved upward into supervision, maintenance, quality control, and system oversight. Unimate didn't end human labor, it ended humans risking their lives for mindless repetition. But progress had a price. In 1972, at the GM Lordstown plant, the unimation of the line led to a 22-day strike. 1,000 workers didn't just lose their jobs, they lost their sense of purpose to a machine that never tired. In 1972, something very different appeared. At Waseda University in Japan, researchers unveiled the Waseda University Robot 1, WABOT-1, the world's first full-scale humanoid robot. Unlike Unimate, WABOT-1 was not built for factories. It was built to answer a question: could a machine move, perceive, and communicate like a human? WABOT-1 could walk on two legs. It could grasp objects. It could communicate in simple Japanese. Its intelligence was often compared to that of a young child. The intention wasn't productivity, it was coexistence. WABOT-1 was humanity's first serious attempt to build a robot designed to live with people, not behind cages, not behind warning signs. But the technology wasn't ready. The robot was slow, fragile, and impractical. The dream was clear, the execution was not. Then, on November 20th, 2000, the world met advanced step in innovative mobility, known as ASIMO. Created by Honda Motors, ASIMO was the most advanced humanoid robot ever built at the time. It could run, it could climb stairs, it could recognize faces and interact politely with humans. For the first time, a robot didn't just work, it performed. Honda's goal was never to replace workers like General Motors did with Unimate. ASIMO was built to explore human-like mobility, to assist the elderly and disabled, and to understand how robots could operate in human environments.
But ASIMO carried a flaw hidden beneath its charm. It wasn't intelligent. Every movement was meticulously pre-programmed, every action carefully rehearsed. If the environment changed, even slightly, ASIMO failed. A stair 1 inch higher than expected was enough to bring it down. ASIMO looked alive, but it didn't adapt. For 50 years, robotics remained trapped in what we now call the era of rigid steel. Machines were strong but blind, precise but inflexible, impressive but fundamentally limited. Robots could execute perfectly, but they could not evaluate themselves. They could not learn from watching the world. And that limitation would quietly hold back the future until the brain finally caught up with the body. For decades, robotics faced a strange and frustrating contradiction. Machines could calculate faster than any human. They could beat world champions at chess. They could solve equations no person could finish in a lifetime. Yet they couldn't walk across a cluttered room. This contradiction has a name: Moravec's paradox. It describes a counterintuitive truth about intelligence. Tasks humans find easy are hard for machines, and tasks humans find hard are easy for machines. Humans struggle with logic puzzles, calculus, and abstract reasoning, but effortlessly walk, balance, recognize faces, and pick up fragile objects. Machines do the opposite. They master logic and math, but fail at perception, movement, and common sense. The reason lies in evolution. The skills we perform without thinking, walking, vision, hand-eye coordination, are the result of millions of years of biological refinement. They are deeply encoded into our nervous system. Abstract reasoning, by contrast, is new, only tens of thousands of years old. So while logic feels hard to us, it's mathematically clean and easy for machines to replicate. Ancient skills are biologically complex. Recent skills are logically simple. That reversal stalled robotics for decades. This is why early humanoids looked impressive, but collapsed the moment reality changed. Take ASIMO. It could climb stairs, wave, and run on stage. But if a step was an inch higher than expected, it failed. The body was ready, the brain wasn't. At the same time, confusion clouded public understanding. Many people assumed robots and AI were the same thing. They aren't. AI is a brain. A robot is a body. Artificial intelligence is software. It recognizes patterns, understands language, predicts outcomes. It can exist entirely on a screen. A robot, on the other hand, is a physical machine. It moves through the real world using motors, sensors, and, most importantly, actuators. A robot doesn't need intelligence. Unimate proved that in 1961. It followed rigid instructions perfectly, forever. But without AI, a robot is blind to change. And without a body, AI is trapped behind glass. The revolution required both. Even with better AI, robots still couldn't move properly, because intelligence alone doesn't create motion. That job belongs to actuators. An actuator is the part of a machine that creates movement. If AI is the brain, and sensors are the eyes and ears, then actuators are the muscles. They convert energy into physical motion. No actuators, no walking. No actuators, no gripping. No actuators, no balance. For decades, actuators were the bottleneck. Robots were either strong but clumsy, precise but weak. High torque, lightweight, energy-efficient actuators simply didn't exist. That's why humanoids stumbled. Their movements looked mechanical, and they stayed in cages. Everything changed in 2012. While the world focused on smartphones and social media, the AI community made a quiet breakthrough: deep learning. Instead of programming rules, we trained machines on data. We stopped telling them what to do and let them learn how to do it. But the real shift came later. We stopped training machines to think and started training them to act. Instead of coding instructions, robots learned by watching humans. Neural networks began to approximate human sensory motor learning. The paradox didn't disappear. We went around it. The trace reaches a critical moment in 2021 when Tesla announced the Optimus program. The world laughed. It was just a man in a suit. But while the internet mocked the demo, something important was happening behind the scenes. The hardware problem was being solved. High-torque actuators, advanced balance systems, precision motor control. Companies like Boston Dynamics and Unitree quietly perfected the body. By 2022, the chassis of the future was ready. It just didn't have a brain yet.
In July 2023, the silence ended. Google DeepMind released the Robotic Transformer 2, known as RT2, the first vision-language action model. This was the brain transplant. It learns from both web-scale data and real-world robotic data, enabling the robot to understand instructions in natural language and translate them into physical actions. For the first time, a robot could look at a pile of trash, understand the concept of recycling, and physically act without being told how. By 2024, progress went vertical. Startups like Physical Intelligence introduced models such as Pi Zero, allowing robots to learn complex tasks simply by watching videos of humans. No code, no instructions, just observation. Then came October 2025, the moment the home robot stopped being a demo and became a product. Figure 03 launched as a general-purpose humanoid, named among the best inventions of the year. At the same time, 1X opened pre-orders for Neo, the first humanoid explicitly designed to be safe enough to live among children. Robots began folding laundry, loading dishwashers, making popcorn, moving with fluidity that no longer looked mechanical. The lab videos were over. The pre-orders were live. 2026 isn't the year robots arrived. It's the year AI learned to stand up. And once intelligence can move through the real world, every job built on routine physical presence is officially on borrowed time.